So now that we've talked about when to use Java parallel streams, let's take a look at the opposite side of the coin, when not to use parallel streams. And again, a lot of this stuff is sort of the inverse of what we just talked about for when to use streams, but it helps to walk through some examples to make the points a bit more clear. So as I alluded to before, parallel streams are not suitable for everything. There are certain types of programs where you don't really get a benefit at all by using parallelism or parallel streams. There's also situations where parallelism might be good, but parallel streams may not be the right thing for you. There's other forms of parallelism that may have less overhead, for example. So one example of something where it doesn't really pay off to use parallel streams is when the data that you're processing, the input source, is expensive to split or inherently splits unevenly. So you can't get it to be split evenly, and you can't get it to be split efficiently. And this example from my EX14 folder in the GitHub account gives an example of this point. So in this example, we're first going to get all the words of Shakespeare, and we're going to stick it into an array list. So that's a pretty big list, as you can imagine. And then we're also going to take that array list and we're going to throw it into a linked list. So now we have two representations of the works of Shakespeare, one that stores them as a linked list, one that stores them as an array list. And then what we're going to do is we're going to go ahead and we're going to count the number of words in those two data structures in parallel. So what we're going to do is we're going to say, array all words dot parallel stream dot count and list all words dot parallel stream dot count. And what's going to happen if you were to run this, you would discover that the array implementation is much, much, much faster than the linked list implementation. And the reason for that is very simple. The linked list approach doesn't scale up because it doesn't split the data structure, the collection, efficiently or evenly. It's kind of a pain. Here's an example. This is the try-split method for the array list split iterator. This is the one that you get for array lists. And this should look pretty familiar to you because it looks very much like what you did for your array split iterator, for your data structure, your unsynchronized array split iterator. And as you can see, it splits the list in half evenly in constant time. So it's super fast and splits evenly. In contrast, the linked list split iterator implementation is much less efficient. It takes linear time, doesn't split things evenly, it splits them off in little chunks, and then it throws them off to a split iterator factory. And so it just takes a long time to run, and you end up with unbalanced results. So no surprise, when you try to run things in parallel, it doesn't work that well. Another reason why parallel streams may not be worthwhile is if the startup costs of parallelism are significantly higher than the amount of data you're actually processing, or, as we'll see in a second, the amount of computation you actually do on each element. So what's an example of this? Well, there is a example. My EX16 folder in my GitHub account has a couple of different implementations of factorial. And you can see here, this is a factorial computation that's going to take in a long, with a lowercase l, and compute the nth factorial using long. And what happens here is that here's the sequential stream version. You can see the sequential stream version creates a stream of longs from 1 to n inclusive, and then it goes ahead and it multiplies them together in pairs till you end up with a single result. The parallel streams version does the same thing, except it does it in parallel. And ironically, even though it's a parallel stream version, the size of n that you can pass in is going to be such that you'll get a poor result here if you use longs, because you'll start to overrun the size, the performance here for small values of n. That's the key point. For small values of n, you actually don't get a win at all by doing it in parallel, because it takes longer to set the problem up than it does just to multiply it sequentially. Yet another variant, which is also demonstrated in this program, is if we had a factorial program that just returned longs rather than big integers, then you can't have a value of n for factorial that's bigger than, I believe it's 23, before you overrun the number of precision, the number of bits in precision in a long, even a 62-bit, 64-bit long. So it'll start wrapping around and you just get the wrong results. So the point here is that this only works if n is big. So if you run the program again and you give it large n, you'll see that you do get a speed up eventually, but for smaller values of n, it won't give you a win to run things in parallel, because that's because it takes a while to split it up and then reassemble it. Yet another variant here, sort of the same issue, just the flip side of the same issue, is the overhead of trying to combine partial results. So if you're doing something that's a parallel stream using a non-concurrent collector, remember you have to assemble the results and combine them. And so here's an example that demonstrates this. We're going to make ourselves a linked list with all the words in Shakespeare. And then we're going to go ahead and, in parallel, we're going to collect this into a tree set. And the way that this is going to work is it's going to end up having to make lots of partial tree sets as it takes each chunk in the linked list, does some processing to it, and then reassembles it piece by piece by piece as it merges all the subresults together. So the actual performance here will be relatively slow, despite the fact that we're running in parallel, because we're merging things back together into tree sets, which are difficult and expensive to merge. Now, you could still get a win here if you did a lot of computation before you tried to merge things together. So I kind of put a ... here saying, you know, not showing what we're doing here. But if we were going to do a lot of processing, we might get a win, because even though there'd be a fair amount of overhead from merging, we still might get a win if we can do computations in parallel. But you're on thin ice, right? And so this goes back to the n times q model. If n is big enough, if q is big enough, if the amount of processing is large enough, then you may still get a win for performance, even though the merging costs are high. A way to optimize this is potentially to use a concurrent collector, like the one that's described here, the concurrent hash set collector. And this can be used to help to optimize the reduction phase, and that's because we just reduce everything into one concurrent collector rather than having to reduce things into sub-collectors and then merge those collectors together. So that might give a win. And I think if you run the program, you'll see it gives you a little speed up to do that with the right conditions. Yet another kind of wacky problem with some of the streams operations, some of the intermediate operations and terminal operations and so on, is that some of these things don't exploit parallelism very effectively. And this is a little bit perplexing when you first stumble across it. And you can discover this for yourself by running the EX15 program to see what I'm talking about. So here's a program where we're trying to go through the first numbers, let's say first 100 numbers, and we're going to try to find the square root of the first number even numbers. And we want to collect it into a list. So here's what we're trying to do. We're going to use a generator function called iterate, and iterate will start with a value, and then it's going to keep generating a result over and over again. So each time it takes the result from before and adds 1 to it. So it's going to generate numbers sort of infinitely. And then in parallel, it'll get rid of the even numbers up to the limit, and then it'll go ahead and find the square root of the first number even numbers. But iterate and limit split and parallelize very, very poorly. And so this program, when you run it, is really, really slow, even though you're running in parallel. You're way better doing it sequentially than doing it in parallel, which is somewhat counterintuitive. But it's because iterate and limit just are not designed to work effectively with the semantics of iterate and limit don't match with parallel streams semantics or implementation. It works, but it's really slow. Here's another way to do this. And what this does is it goes ahead and we'll go through the first number times 2 plus 1 numbers in parallel, filter out the even numbers, and then calculate their square root. And this will run really fast because range splits nicely and runs very efficiently in parallel, whereas iterate and limit do not. So that seems a little counterintuitive at first, and you have to kind of read the documentation carefully to learn why this doesn't behave in the way that might seem most intuitive. But it just goes to show that implementation details do matter. Another kind of obvious reason why parallelism might not be worthwhile is if you don't have many cores. If you're using older computing devices that only have a single core, you're just not going to get much, if any, speed up, especially for compute-bound tasks. You might still get a little speed up for parallel processing of I/O-bound tasks, but the more cores you have, obviously, the more likely you're going to do things better. And yet another kind of wacky issue is that there's no easy way to shut down the processing of a parallel stream. So once a parallel stream starts to run, it's difficult to tell it to stop. And you have to play all kinds of little tricks by like setting flags that you then test in your behaviors to see if the shutdown flag has been set. And if you do that, you have to make sure your shutdown flag is a volatile, and then if something goes awry, you have to throw an exception and catch the exception. So it just gets complicated very quickly. So just be aware of that once you start the wheels in motion with a parallel stream, it doesn't make it easy to shut down. OK, so that kind of gives you a sense of when not to use parallel streams.